Uh, Welcome back to Transcended. So we're going to answer these questions from a functions tutorial sheet. So we have a question one there which is asking us to look at these arrow diagrams and identify them whether they are functions or not. And then we have question two where we've been given g of x. We are told to answer all that. With question three there, we have question four, we have question five, and many more other questions. Okay. So before we could get to answer all these questions actually, I would just like to make some things known to you about functions so that even as we try to answer, we answer together. So I will not basically edit this video because I want to approach your questions as you would approach them as well. So the first question you'd want to ask yourself is what exactly is a function? So there are these two terms that you're going to meet in this tutorial sheet, a relation and then also a function. So one thing that I would want you to know is that all functions are relations, and then not all relations are functions. So it's like you've got this big set called the relation, and then within that set there are some relations which are also called functions. Okay. So of course you know what a relation is because I'm sure you know what relationships are, right? It's like there's a connection there. So usually what we use when explaining this, we usually use x and y, where we usually call x to be an input value and then y to be an output. We usually use these and then we perform kind of a mapping there. So mapping basically just demonstrates the relationship that is there. Okay. So if we can have 1 and 2 there, and then basically you can have, let's say, a 2 there and a 4 there, and then I map them like this. So you're able to agree with me that the relationship that is there between x and y is x mapped onto y. What you're saying there is y is going to be what? It's like it's supposed to be doubled, right? It's like x squared. Not x squared, it's to be 2x. So now to be smart about it, I would have to say, I would have to put it this way. Y is equal to 2x. So if we've got the value of x, if I plug in there, I should be able to get the value of y. So that is an example of a relation. And of course, it is a function. Now, what exactly is a function? And how is it different from all relations? So, what you need to understand, a function. A function is of course a relation. So, a function is a relation where every input has a what? A result. So what result is what? An output. So every input should have an output. Okay? And that output should be unique. Okay? Unique output. What that means is, in cases where you have, let's say, A, and then it's giving you different results, that is not a function. You expect that A should only be able to give you one result. Okay? An example of a function is if I give you an equation x plus 2. Okay? So if I'm trying to find the value of y, I should just plug in the value of x there. So f of 2 is equal to, where there's x, I'll put a 2 plus 2, giving me a 4. That's an example of a function. So I don't expect to put the same value 2 in that function and then get two different results when it's not a function. That's a basic idea there. Now, we'll look at question 1 and try to identify some of these. We'll disqualify some of them. Okay? At least from what we've talked about. So question 1 says state which of the following relations given by the arrow diagrams are functions. So we'll look at A first of all. Let's try to observe A. So this is our input. They are all mapped to something, and they are all mapped to unique things. So of course I would like to mention to say a function where every input or where every output is mapped onto something is called an onto function. Okay, and then where each one is mapped to a unique one again, it's also called one to one. So in this case we have a one to one function. It's a function because every input has an output. We go to B. Is it a function or not a function? I think you've seen the key term I've been using. Every input should have an output. So in this case B doesn't have an output. So this is not a function. B is not a function. If you look at C, A, B, C, D. Now this is where it becomes tricky. This is where it becomes tricky, and most of you are already lost there. Is it a function or not a function? So every input is mapped to an output. Is it a function or not a function? So in this case, this is also a function. It is a function because every input has an output. So is it possible for you to have many inputs having the same result? It's very possible. I like giving this example. F of x is equal to x squared. Do you agree that if I was to use 3 and negative 3 as my input values, for 3 squared it will be 9, for negative 3 squared it will also be 9. Is it true? So this is proof enough that it's possible for us to have different input values giving us the same output. So we actually call such a function to be a many to one function. Okay, so a many to one function. But we don't have what we call one to many function. Now it becomes a disqualification where you are using 3, for example. In the same function you put 3, in the same function again you put 3, and then it gives you different values. Let's say 7 and then negative 7, same value. That doesn't exist. That's what we reject. Okay, so if this was the opposite, if we had the 4 being mapped to different things, it doesn't exist in such a case. Don't mix up information there. Very, very important. Okay, we're now on D. What do you think? Is it a function or not a function? So observe the way the inputs are working. A, B, C, and D. So A is mapped to 3, B is mapped to 3 as well, C is mapped to 1, D is mapped to 1. So at least everything in the input is mapped to something. And then we've already talked about that case. It's possible for 2 input values to give you the same output. So that is still a function. Now some of you have already been observing that from C we've got no issues by having output values without an input. That's not a problem. It's possible. Of course, under programming, I would give you such examples. For example, if you're checking the time, right? What's the current time? Current time is, of course, that is under programming. But of course, think of it in real time. Like, if you're checking the time on the clock, or if you ask someone to say, what's the time? They'll just tell you if it's 14 hours, 14 hours. There is no input value there. Or even if you're checking your phone, you don't have to put any input value for you to get the time. You just check the time. So that is an output directory with no input. And then we'll go to E. Observe A, B, C, D. So the basic definition of a function, I was saying every input value should have an output, right? So in this case, A and B don't have outputs. So it is not a function. Then the last one, A is mapped to 4, B is mapped to 1, C is mapped to 3, D is mapped to 2. So this is also an onto function, one-to-one function. So at least every input is mapped to something in the output. And we don't have a case where an input is mapped to 2 things. So if we can have B mapped to 2 different things, then it is not a function. Okay, but in this case it is a function, unless otherwise. Okay, so that is just a basic introduction to identifying relations which are functions and which ones are not. Okay, so later on we'll look at how to prove an onto function, how to prove a function is one-to-one. We are now on question 2. Question 2 A says, given that the function g of x is equal to that, find that. So that one is very simple for all of you, but I'll still answer. So functions are not as hard as people make it look sometimes. Some even just math generally, like there's just this misunderstanding, this belief, this myth around that it's complicated. Just take time to understand certain principles, the basics, you'll be able to, you're home and dry. So the way you basically get to do with functions, these are things we've been dealing with from high school. So if you look at part 1, which says g of 4, what that means is where there's x, please put a 4. So I'm just following g of x itself. So we have x squared there, so I'll put 4. Where there's x, I'm putting the 4 minus 6. What's the answer? 4 squared is what? 4 times 4 is what? 16 minus 6. The answer is 10. Part 2 says g of negative 4. This is where you have to be very careful now. Your x is negative 4. Now it is still squared, minus 6. That is still 16 minus 6, 10. Now this is a case where I was talking about to say it's possible for you to have two different input values but have the same result. It is still a function. And then finally we have g of 2. G of 2 requires us to substitute a 2 where there is x. So 2 squared minus 6. 2 squared is a 4. 4 minus 6 is a minus 2. So we've answered question 1 to question 2a, 1, 2, 3, and then we're on 4. Find the possible u values of a. Possible values of a. So this was supposed to be if g of a is equal to a. So I can erase this. I believe you've understood how to go about all that. I was expecting them to put at least the inverse part, where they say find the g negative of x. So cover that later on. So we are saying g of a is equal to a. So what does g of a mean? G of a means where there's x squared, put what? A, right? So in such a case, on the left we're going to have a squared, where there's x, I've put a minus 6. Then it should be equal to a. So now this takes you to a quadratic function. You you take them on one side, it will become a minus a, and then minus 6 equal to 0. So usually, for me, the first option I usually take when I'm trying to solve a quadratic function is, first of all, I'd have to try out if it's possible for me to factorize that. So the product is, you look at the coefficient of the squared part with the constant. So negative 6 times 1 is, so my product is negative 6. My sum in between is the coefficient of the middle part, which is a negative 1. Think of two numbers that you can multiply to give you the negative 6, you add them to give you a negative 1. So I can personally think of 3 and a 2. I just need to understand now where so if I'm adding, getting a negative, it means the negative is supposed to be on the bigger number. That's why I said this video I'm not editing. I'm trying to use a language that everyone is familiar with. So negative 3 multiplied by 2 is negative 6. Negative 3 plus 2 is a minus 1. So those are our two factors. So the way it works is, those ones will substitute the middle part, right? So I have a minus 3, and then you have in the other bracket a plus 2 equal to 0. So if you try to make a, you get what is in the brackets now equated to 0 separately. So this one will give me an answer of a is equal to positive 3. The other one, a is equal to minus 2. So these are the two possible values of a. Okay, so that's it with question 2a. So if you are one of the people who wants to learn this topic from like scratch, there's a link in the description there. There's also the WhatsApp link to the WhatsApp group, and then there's also the contact, the person you can get in touch with if you'd like to have access to the videos from scratch and also attend the classes. where you get to learn everything in details and you have access to all the tutorial sheet questions, solutions that is. And then B, f of x is equal to 2x plus 1. Find f of x squared. I think it's just about understanding the language that has been used now in this case. So what it means when you say f of x, and then for me I like using parentheses for that, or different brackets actually, the square brackets, I call them square brackets, squared. So I want you guys to understand that there's a difference between that and then it's different from this, where I say x squared. This language means whatever is inside those brackets, it means you substitute where there's x in the function. Now, when you square the entire function, including the f itself inside there, it means that what you're doing is this. So substitute, what do you know in this case? You know that f of x itself is 2x plus 1. Now what are you doing is you are squaring this. That's what we are doing. So perform this normal algebraic multiplication. So we have 2x plus 1 multiplied by 2x plus 1. So let's try to multiply that. 2x times 2x is 4x squared. 2x times 1 is 2x. So it repeat to be 4x and then plus a 1. So that's our answer. So this is what I was trying to say, that this is different. I didn't even pay attention that it was there. So that is our first part. It's very windy where I am. Just close the window. And then we are on the second one. F of x squared. This is different. I said what that means is where there's x, you basically get to substitute x squared. So you have 2. Now where there's x, we'll put what? We'll put x squared and then plus 1. So you end up having 2x squared plus 1 as a result. And then the other one, which is like the last one, very interesting. So feel free to pause the video and just try that one out. So we have f of x. So what does that mean? So what it means is it's like you still have the normal function. Now the input value is the function itself. That's how interesting it is. If you still want to understand it more, you can even write the function itself, which is 2x plus 1. Now where is x, we are putting what? F of x. Now don't forget, in the function we've got 2x plus 1, so it is plus 1. So now f of x is the input itself. So the function itself is 2x plus 1 plus a 1. Don't forget. So you have 4x plus 2 plus 1, giving us an answer of 4x plus 3. Okay, so that's it for question 2. We are now on the third question. I've not even paused the video. I'm just still going on. No editing. Okay, so just taking some water. Question 3a. The function g is given by g of x is equal to x squared minus b, where a and b are real numbers. If g of 2 is equal to that, g of negative 1 is equal to that. Find the values of a and b. So each time you're looking at all these, think of quadratic simultaneous equations. Yes. So pause the video and try that one out. So you've got g of x being equal to ax squared minus b. That is your function. Now for the first one, we've said g of 2 is negative 5. G of 2. So I'll write that g of 2 is equal to negative 5. Now, g of 2, what that means is where there's x, you put the 2. So we'll look at the function itself. So I'll say a, where there's x we are putting a 2, so it will be 2 squared minus b. So now we know that g of 2, the result in the question has been given to be negative 5. So put negative 5 on the left. Is that a 5 or it's an s? So negative 5 is equal to, now 2 squared is 4, so we have 4a minus b. So we have our first equation. And then I'll use white for the other part. So we have g of negative 1 as well. So what that means is in the function where there is x, you put negative 1. So for the g of negative 1, the question tells us the answer was a 2. So equal to negative 1 squared is 1. So it will just be a minus b. So we have these two quadratic. We've got these two simultaneous equations because we expect that the value of a and b should be the same in both equations. So for me, I feel working with the one on the right is easier, where I can just make a the subject by taking b the other side, so that we have 2 plus b is equal to my a. So I've made a the subject, and then I'll come back to this other equation where there's my a, I'll put that. So for a, now where there's m, I'll put 2 plus b minus the b, which is coming from there. So at that point, we just have b, we're able to find b. So we've got negative 5, 4 times 2 is 8, 4 times b is 4b minus b. Can collect the like terms. On the left, I can take 8 there, so that it becomes negative 5 minus 8, which I believe should be able to give us what? What do you get if you add 5 plus 8? You get the 2 from the 5, it gives you 10, you remain with 3, so it will be negative 13. And then 4b minus b, it gives you 3b. Divide both sides, your b becomes negative 13 over 3. I'm not so comfortable with finding fractions, but anyway, that's what we have. So for me to find the value of a, I'll just go back to the other one, which is 2 plus the b. The b in this case is minus 13 over 3. So the faster way of simplifying that is multiplying the 3 by the 2, or you can come with a common denominator. It's the same. 3 times 2 is 6. 6 minus 13. What's that? 6 minus 13. So the difference should be minus 7. So negative 7 over 3 as your answer. So we found both values of a and b. We are now on question 3b. So find the range of each function for the given domain and state if a function is one-to-one or not. So in case you don't know what a one-to-one function is, I'll just give you an example. So a case where you have a domain matching up the codomain, where every element in the codomain is mapped onto one single item in the input, that is a one-to-one function. Now in a case where we may have two elements, let's say I introduce another member of the domain and then it matches to the same result. Such usually happens in a function x squared, where you can have negative 1 and it's positive, giving you the same result. So that is not a one-to-one function. Okay, so try to answer the question. So the first part is f of x is x minus 2. That is for the first part. So the domain has been given to be negative 2 all the way up to 4. Now that is, they are included because it says less than or equal to, yes. So now, if you want to answer these questions very fast, you would want to come up with a table of values. Now, for the table of values of this kind of a function we have is a linear function. Now the way a linear function behaves is this. If I was to sketch one, it would be something like this or something like that. So that already proves to say there is no possibility that you may have a linear function giving you a y value of the same between two different inputs. It's not possible. So looking at this example, the other beauty about a linear function is if I just get the value here, the starting point of x and the one there, I'll be able to get the range. That's the beauty about a linear function, because it increases or reduces at the same rate. So in this case, finding the range means, in case you still don't understand what it means, finding the range means we are determining the expected values of x to be produced by such a function. So if that is my linear function, the value of y at this point and the value of y at the highest point, the values of y, that is the range. The domain are the values of x from there all the way up to that point. So we've been given the domain from -2 all the way up to, so maybe it's somewhere there, all the way up to 4. So all we just have to do is just substitute for a linear function. So the minimum we have is a -2. So -2. The highest we have is a 4. So how do we find the value of y? We substitute in the function. So if I put a -2 there, we have a -4. If I put a +4, we have a 2. So that implies that is the way that linear function is going to move. So the expected values of y will be -4 as the minimum all the way up to 2, given that domain. Alright, so we'll move to B. So of course it is 1 to 1, because whenever I draw a linear function, it's not possible that two different values of x will give you the same value of y. So they'll be unique at each point. So it's a 1 to 1 function. Okay. So another way you can prove that it is 1 to 1, there's a way you're supposed to prove a 1 to 1 function. So our function itself is f of x, excuse me, being equal to x minus 2. So we need to prove that if you were to have a function at a being equal to, let's say, c, and then you also get to have a function at b also giving you c, we don't want this to occur. We only want this to happen if they are the same, if a and b are the same, not being different numbers. Okay, so let's try that. So if I was to have f of a, my f of a, let me say, in this case a is supposed to be equal to b for that to be possible. So f of a is going to be a minus 2, f of b is going to be b minus 2. So I equate them. A minus 2 is equal to b minus 2. So therefore a is equal to b. So this only occurs, it's not possible for two different values of x to give you the same value, only if they are the same. That's the main idea of a 1 to 1 function. Hopefully you get that. So this is proof that it's a 1 to 1 function. We are on the second one now. F of x is equal to x squared. So the domain has been given to be from -3 to 3. So this is a quadratic function. I believe it's not new to you. So we can also try to see the way it's going to behave. So we've been given values like from -3. So I'm coming up with a table of values, and I'm also teaching you guys how you can first sketch functions. If they ask you to sketch, they do ask that. So I'll get a 0 in between and then a 3. So my expected value of y, I'll just substitute in the function. So if I put a -3 squared, it will give me a 9. 0 will give me a 0, 3 will give me a 9. So we are saying that we've got two different values of x giving us the same value. Now the other thing that we have to pay attention to is our domain in this case is not including -3 and +3, because it is not less than or equal to, it is just greater than and then less than, that's all. So what then should we do? So in this case, if you are to sketch this function, you know the way quadratic function behaves. So whenever the value of x squared, the coefficient is positive, you need to understand that it's going to be a minimum parabola. Okay, now the minimum value this expected is going to be 0 for this function. 0, 0 give us 0, and then to continue going up. Okay, so a function where I'm able to draw a line a horizontal line and then it cuts the graph at 2 points is not a one-to-one function. Okay, so the expected range, the minimum value we have is 0, 0, and then it will just continue going up. Now restricting the domain to a point where we're reaching only at 9 or at 3 would mean that it's ending maybe, let's say, somewhere there. This is negative 3 and this is positive 3. It's only ending at 9, so we can't go beyond. Now the fact that negative 3 and positive 3 were not actually part of the domain because of just being less than without an equal or a dash down, the range will be restricted from 0 all the way up to 9. 0 is part of the range, but 9 is not, because 3 and negative 3 are not part of the domain. So that shows that less than 9, but 9 itself is not part of the solution set. Now the other way, when you're looking at quadratic functions, you can just like use the formula for finding the minimum value. Negative b is equal to, so our b in this case is obviously 0, right? So you have 0 over whatever you're going to have is 2 over 0, and then to get the value of y, you substitute it, also give you a 0, so it is 0, 0 in such a case. That's a minimum point. So a maximum is dependent on the values you have. But if there was no restriction on the domain, if let's say the domain was just a set of real numbers, it was going to be from 0 all the way up to positive infinity. And in such a case, without a restriction like that, the answer would just be from 0 and then positive infinity. Of course, infinity can never be part of the solution set. We are now on the third one. So first of all, I've disqualified the second one. It's not a one-to-one function. It's not a one-to-one function. Okay? So you can actually try it out. F of a is going to give us a squared, and then f of b is going to give us b squared. So we need to so we'd have to prove that if f of a is equal to c and then f of b is equal to c, then we should get the same result. Then actually a should be equal to b. So a squared is equal to b squared. So these are not equal, right? They are not equal. A squared is equal to b squared. They are not equal. So in this case, it is not. I showed you negative 3 and positive 3 were giving us the same result. Even just the fact that if you sketch it, if you draw a horizontal line, it's cutting the graph at 2 parts. So it is not a one-to-one function, or it is not an injective function. So a one-to-one function is also known as an injective function, for your information. Now going to the third one, where we are saying x is greater than 1. X is greater than 1. So quickly we can just like come up with a sketch fast. So the function itself is 1 over x minus 1. 1 over x, how am I writing there? X minus 1. So x, y, a table of values, just to estimate things here. So we are saying the domain is restricted to values of x that are greater than 1. So greater than 1. So the derivative will start from 1 itself. So if you start from 1, you see that it will give you a 0 on the bottom, so it is not defined at that point. So if I try derivative 2, or let me say 1.5. So 1.5, if you substitute the 1.5 minus 1, it will give us 0.5. 0.5 into a 1, it's going to be 2 times. If I put a 2, 2 minus 1, what will be the answer? 2 minus 1 will be 1. Into 1 it will be 1. So 2 will give us a 1. If I put a 3, 3 on the bottom will give us a 2, so it will give us 1 over 2. So 1 over 2 is like 0.5. So we are now seeing what is happening to the graph. So if we were to sketch this graph, So this graph can never cut this line where we're saying it's x should be greater than 1. So it cannot actually, it can never be equal to 1. So that becomes what we call the asymptote, the vertical asymptote at x is equal to 1. Now we've tried values like 1.5, and then we've tried 2, we've tried 3. So what have we observed? For 1.5, it has given us 2. So let's say 2 is there. 1.5 has given us a 2. And then for a 2, it has given us a 1. So let's say 1 is somewhere there. And then for a 3, it has given us a 0.5. So what are we saying? This is 1.5, that is 2, 3. So as we continue, we expect that the graph will be getting closer and closer to the x-axis, like that. But it shouldn't cut. And then that will continue going up as you get closer to 1. So in this case, we are saying that in terms of the values of y, we are getting closer to 0, and then we are also increasing towards the infinity. And then both are not part of the solution set. So that's the range. The reason being is we will not cut the x-axis, and then we shouldn't get to meet the asymptote. So continue going up. And that is true. As you've seen, as we are getting closer to 1, from reducing, we are seeing that the values of y are increasing. So if we are to get a number like, let's say 1.1, and then ask yourself 1.1 minus 1, it will give you 0.1. 0.1 divided into 1, it will give you a 10. So values will continue increasing as you get closer to the asymptote line. So that is our range for that function. So is it a one-to-one function? Of course it is. So there's no way you can draw a line this function and then you expect that it will cut the graph twice. So it's a one-to-one function. So by the way, they didn't ask you to prove, so you can just state it is a one-to-one. And then for the last one, f of x is equal to 1 over x squared plus 1. How do we handle that one? So for that one, what we'll do is we'll do the same. Now here the domain is a set of real numbers. Now the moment I look at x squared, for me what comes to mind first of all is it is not possible for us to ever get a negative number in this case. So that's why the domain is actually a set of real numbers, because it is not possible that you can get a negative 1 to give you a 0 on the denominator because of the squared part or any even power. Okay, so that is a good starting point. Now the other thing that you need to think about such powers is it doesn't matter whether you're on the negative numbers or the positive numbers. These are the graphs that come out like this. Okay, now let's try to see this, how this one is going to come out. So come up with like a small we'll come up with a small domain, like a table of values x, y, and then we'll use the values, let's say I'll use 2, negative 2, negative 1, 0, 1, and 2. So expect negative 1 and negative 1 on the opposite signs to give us the same result. So if I was to put a 0 on the denominator where there is x squared, I'll just have a 0 plus 1, which is a 1. 1 into 1 will give us a 1. And then if I put a negative 1, negative 1 squared will be a 1 plus 1, 2. So 1 over 2, which is like 0.5. So expect the same for the other side. Now if you put a 2, 2 squared will be 4 plus 1, 5. So it will be 1 over 5. Now 1 over 5, if you know mathematics, it's 0.25. I believe it's 0.25. Yes. So yeah, pretty much that's where we are now. So if we were to sketch this graph, how is it going to come out? So we are seeing that the highest value so far we have is a 1, which is happening at 0, 1, 0, 1. And then after trying the other values like negative 1 and positive 1, they've given us 0.5, so which is like half, somewhere there. and then after trying out the other values 2, -2, again it is getting down and down. So what are we seeing in this function? So I'm seeing this function to behave like this, that being the highest point, and then to continue getting closer and closer to x. So already from the graph we're able to see that this function is not one-to-one, because if you draw a line it will be able to cut the graph twice. So like we've seen actually from the table of values, two different values are able to give us the same value in the codomain. So that is not a one-to-one function. Now what can you say about the range? What can you say about the range? So of course if you try to find the range of that function, you notice that the graph actually, the line will not actually get to cut, it will not get to cut it's not possible. The reason why I'm saying it can't cut the x-axis is because we can't get a negative result in such a case. No matter what number you're going to put where there's x squared, you can't get a negative value, okay, because that is also positive. So the expected range is the highest value to be 1, and then all the values to be between 0 and 1. So 1 is part of the solution set, but I believe 0 will never be part of the solution set. So you can try to come up with the range of that function. You find that it will become something like a square root. Yeah, you can try to find the range. So this is actually the actual graph that you can have a look at. That's the way actually this function will behave. So from that value of y going closer to 0 but never equal to 0. We are now answering question 4. So we'll be a bit fast. So find the domain and the range of the following functions. So how do we handle that? So looking at a, f of x is equal to 1 over x squared. So what you do is where there's f of x, you put y. So y is equal to 1 over x squared plus 1. So we need to find the domain and the range. So the domain is made up of values of x that are able to define that function. So the first way of thinking about your answer is ask yourself a question to say, is there any value of x that can make this function to be undefined? Okay. So of course there are certain parameters that we look at. In case where you have a fraction, for example 1 over x, you want to ensure that the value of x will never be equal to 0, because you can't divide a 0 into a number. The other restriction is if you have a square root of, let's say, x. Under the square root there, you can only find the square root of a 0 and a positive number. So negative numbers are also to be avoided. So those are the few restrictions that I can mention of even as we start. So if you look at x squared plus 1, in this case we have a fraction. So for a fraction, we want to ensure that our denominator, which is x squared plus 1 in this case, should not be equal to 0. So if you take 1 the other side, it should not be equal to -1. Now, you would have to be smart about this. If you look at our x squared there, whenever you have x squared and then it's positive, or whenever you have an even power, you understand that in such a case, you will never be able to get a negative. And if that is the case, if you never get a negative, and then you have an addition sign there, so you can't ever get a 0 on the denominator, because x squared can never be equal to -1. It's not possible, because if you try to find x there, x should not be equal to the root of -1. So it's not possible that we can have that value. So in this case, there is no value of x that can make this function to be undefined. So therefore, the domain will be the set of all real numbers from -infinity all the way up to +infinity. That is our domain. How about the range? How do you find the range? So you get to find the range by making x the subject. So the inverse function is what will help us to find the range. So if I try to multiply, cross and multiply, I'll have y x squared plus y being equal to a 1. My goal is to make x the subject. So I can get the part having y, go the other side, so that we have 1 minus y, and then we can divide both sides by y, right? So that we have our x squared being equal to 1 minus y divided by y. So finally our x becomes 1 minus y over y the square root. So of course plus or minus. Now the question is, if you look at this square root that we have there, the value of y denotes a range. So what value of y can make this function to be undefined? Of course, if they had asked you to find the inverse function, you don't have to leave it in that form. You have to take it back to this form. Now, where there's y, you'd have to put your x and whatnot, like that. That would be the inverse function. Now, I like leaving it in form of y when they have not asked me to do so, so that as I present my range, I'll use the value of y. So the way you look at it is the same way. The same way we're finding the domain of the original function is the same way we're going to find the range. So think of it. What value of y can make that function to be undefined? So the fact that we have a fraction inside there, first of all, y, which is the denominator, should never be equal to 0. That's the first part. Now the fact that we have a fraction there, the fact that we have got a square root, we need to ensure that 1 minus y over y should be greater than or equal to 0. Greater than or equal to 0 means positive numbers including 0. So if you ask yourself a question, how can we solve this inequality? 1 minus y over y should be greater than or equal to 0. I can do this. So one way of solving that inequality is, think of what value can make this the left hand side to be equal to 0. So the denominator, if the denominator was going to have a 1 there, if y can be equal to a 1, we have 1 minus 1. So the value of 1 will be used as our determinant. And then we can also use something we are avoiding, which is a 0. So 0 is obviously on this part. So I'll try values greater than 1. Let's say 2. If I plug in a 2 there, 2 on top, I'll get a negative. So I'll get a negative value. So this part doesn't qualify to be greater than or equal to 0. Now if I get a number less than 0, let's say negative 1. On top, I'll have 1 minus negative 1, which will be a positive. Now for the denominator, what am I having? The denominator will also have to have a negative 1. So I'll still get a negative result, which also doesn't qualify, surprisingly. But if you try to look at the value between 0 and 1, let's say 0.5. 1 minus 0.5 over 0.5, the numerator will be positive, and then the denominator is also positive. So we can say somehow the middle part is agreeing to that idea. So we can say that the expected values of y are to be between 0 and 1. Okay, so between 0 and 1, but 0 itself is not included. So it says 0 is less than y, but y is less than or equal to 1. We're now on B. So f of x is equal to 1 over x minus 1. So our y is equal to 1 over x minus 1. So think of it, this one is also a fraction. So first, our denominator should never be equal to 0. So if that's the case, x should never be equal to 1. because if x is equal to 1, then the denominator will be equal to 0, making the fraction to be undefined. So we are trying to avoid all that. So we can say now, every time you're trying to find the domain, try to find out what values are you able to remove from the set of real numbers. So x is a member of real numbers, but x should not be equal to 1. The other way of presenting this result is negative infinity all the way up to 1 unionized with 1 all the way up to positive infinity. That's another way. So in case you find that somewhere, don't be surprised. So again, for us to find the range, the faster way of doing so is by making x a subject. So if I close and multiply, that will be my result, and then my goal is to make x a subject. So I have 1 plus y, and then x becomes 1 plus y over y. Okay, so of course I told you how to present your inverse. So f of negative inverse will be equal to 1 plus x over x. Now in this case, finding the range, we just look at that. So we are saying that this being a fraction, y should never be equal to 0. So therefore, we expect that the range will be all values. So y is a member of real numbers, but y will not be equal to 0. So instead of putting y, you can also put the value of f of x to denote the range. We now have a radical function, which is c. Y is equal to square root of 1 minus x squared. So whenever I've got a square root, you need to ensure that the denominator do we say the denominator, whatever is under that square root, should be greater than or equal to 0, because you can't find the square root of a negative number. So how do you solve that inequality? How do you solve that inequality? 1 minus x squared should be greater than or equal to 0. How best can we handle it? So think of it in this way. What values of x are able to make this left part to be equal to 0? So I feel if I put a negative 1 there, I'll get a 0. If I put a positive 1, I'll also get a 0. So I'll use those two numbers as my zeros, negative 1 and 1. And then I'll try substituting. So I'll think by the number in between, 0. If I put in a 0 there, it will agree. 1 minus 0 squared will be a 1, which is greater than 0, right? So this part has agreed. What if I try, let's say, a negative 2? If I put in a negative 2, I have 1 minus 4, which is a negative, which has refused. Okay. If I try the other side, it will also refuse. So the expected domain is negative 1 is less than or equal to x. X is less than or equal to 1. We only expect our values to be between negative 1 and 1 if we are to maintain a positive value or equal to 0 under that square root. Okay, so we found the domain. How do you find the range, the expected possible values? Before we try to answer, you can try to give it a guess without solving. If we're only putting values between 1 and negative 1, the fact that we have a 1 leading there, it means I'm expecting that the values first of all will just be between 1 and 0. That's the way I feel. 1 and 0. Yeah, that would be the expected solutions. That's just me expecting that. Let's try it out. So you can try to make x a subject. So square both sides, we'll have y squared is equal to 1 minus x squared. We'll have y squared minus 1. Sorry, I'm trying to make x a subject of the formula. So if it goes the other side, it will become positive. And then we'll have 1 minus y squared. And then x will be equal to So it also becomes a square root 1 minus y squared. It's kind of like we've just like exchanged, right? It's like everything has just gone back to the same procedure. So all the same, we don't want us to have value of, so if we want our denominator to be greater than or equal to 0, so that is only possible if we use -1 and we get the numbers between -1 and 1. So now, thinking about this in a smart way is that the possible values of the range, or the possible values of y we should expect from that radical function, are 1 being the maximum number, but then we don't expect to have a negative number. So in this case, using the inverse function may not work necessarily perfectly. Just think about this. All the numbers we are putting where there is x squared are subtracting from 1. So the expected minimum value that we should expect is a 0. So 0, the maximum value is a 1 itself. So that's our range without wasting your time. Because if you say no set of real numbers except what and what, that's wrong. Let's be realistic. If we are to, the other way we can do it is try to sketch a function. So if you try to sketch, of course, if you put a 0 there, 0 will give us a 1. So that's where we're starting from. 0, 1. If you put a 1 there, if you put a 1, you get if you put a 1, you get what? You get a 0. What else? So 1 is the maximum number we are going for. Yes, 1 is the maximum number we are going for. If we put a -1 there, if we put a -1, we equally get a 0. We'll get a 0. Now, it's not possible for us to ever get a negative number. So this is the behavior of this radical function, surprisingly. So 1 maximum, 0 minimum. We're now on number what? Number D. Letter D. So what one is actually the opposite of what we're from talking about. So y is equal to root of x squared minus 1. For this one as well, we don't want our x squared minus 1, which is like under the square root, to be ever be less than 0. So it should be greater or equal to 0, meaning that we're interested in the positive numbers. So equality, that's an inequality. So the zeros of that inequality is also -1 and +1, because if you put a -1, we'll get a 1 minus 1, 0. If we try what is in between, if we put a 0 there, we'll have 0 minus 1, which will also, this time around, it is disqualified. It has refused, because we get a negative. That part will be eliminated to get a -1. But if we try numbers after 1 and less than -1, they'll work. For example, if I try -2, -2 squared will be 4 minus 1 to give me a 3, which is indeed greater than or equal to 0. So the moment the middle part refuses, the other two parts usually agree. So therefore, our domain are values of x less than or equal to -1, values of x greater than or equal to 1. Those are the ones that are able to give us a 0 there, and also numbers bigger than 0. Now, you're already able to tell to say, okay, since this function is starting with x squared, and then the value of x are, since it is the power 2, there will always be positive values. There will always be positive values there. So this function is expected to be increasing. It is expected to be increasing continuously. And of course, radical functions, the minimum values you can never have is always a 0. So you have x squared minus 1. What value can give us a 0 there? 1 itself. So at a point 1 and a point negative 1, the function is at what? Is at 0. So 0, 0. If you put a 2, you get a 4, which will give us a 3, like that. I believe radical functions go like this. So I'm expecting this one to be going the other side like this. So these are like reflections of each other because of x squared. So this is not actually a bijective function. It is not one-to-one. So what are we seeing? We are seeing that the values of y are increasing. The minimum value we have is a 0. So the range is from 0 all the way up to positive infinity. That's for the range. We have an interesting one again. F of x is equal to, so y is equal to root of x squared plus 1. For this one, it is more related to the first one we had. You understand why they are related. So we have x squared plus 1. So is it possible that we can ever get to a point where we have a negative on the under the square root? So the fact that we have a positive 1 being added, it was only going to be possible for us to get a 0 or a negative number if we had an odd power there, because no matter what you plug in into the value of x, we always get a positive value. So we can never get a negative, not even a 0 in that case, but a 0 can still work. So there's no restriction to our domain. So our domain is a set of all real numbers. All real numbers can work. Now, what are the possible values of x, values of y expected to come out of that? So with that understanding, we understand that this function we have will never give us a negative result. And of course, if we are to plot, let's say we put a positive 1. If we put a 1 there, you get 1 plus 1, which will give us a root of 2. Again, if you try the other side as well, also get a root of 2. If you put a 0 there, you get a 1. So root of 2 and 1, which one is bigger? Mathematics. So 1 times 1 is 1. The root of 2 is bigger. So say I have a 1 there, and then root of 2 is somewhere bigger. So if you try a negative number, you've seen that this is the way the graph is behaving. Something like this. What can we say about this graph? The minimum value we can ever get under this square root is when x is equal to 0, which is a 1. So if x is equal to 0, we'll get a 1. If you try to put a negative number or a positive number other than besides 0, you basically get to begin going up, because you'll be adding something to our 1. So the range is, the minimum value is 1 going up to infinity. That's the range for that function. By the way, if you have questions, you can always type them in the comment section. We are now on f of x is equal to 1 over x, so y is equal to 1 over x. This one I already talked about it. X should never be equal to 0 when you have a fraction. So our domain is a set of all real numbers, but x should not be equal to 0. That's our domain. Our range, we try to make y the subject or x the subject. X will be equal to 1 over y as well, so it's the same. So we expect that y is a member of real numbers, but y can never be equal to 0. So 0 is excluded from the codomain. So we can try even to sketch that so that you have a picture of what I'm trying to say. So 1 over x, let's say we want to sketch that function. So we'll try to start from -2. If you put a -2, you get a negative 0, you get a negative 0.5. If you put a negative 1, you get a negative 1. If you put a 0, it can't work. If you put a 1, it will give you a 1. If you put a 2, you get a 0.5. 0 is undefined. 1, 1, negative 1, negative 2, positive 2. So x is equal to 0 is what? The vertical asymptote. The other asymptote is what? If you make your inverse is also 1 over y, so y is equal to 0 is also our horizontal asymptote. So I expect that this graph will come out like this, and then like this. Like that. So that's why if I put 1 comma 1, it's there. 2, it's getting closer to 0. So the more I begin going up and up, the numbers will be getting nearer and nearer to the x-axis. The moment I begin getting closer and closer to the value of 0, for example, if I get a 0.1 into a 1 to give me a 10, so it will be going higher and higher. The opposite is true this side. So this is the behavior of this graph. Now the question is, what is the expected value of the range? So we are seeing that this graph is going towards a positive infinity. It's also going towards a negative infinity in terms of our y values. The only value that we can ever get is 0. We are only running away from 0, but we are going towards a positive infinity, negative infinity. So all set of real numbers except y is equal to 0. For the value of x, we can also see that all the values of x are working, going this side and going the negative side, but except 0, which is being avoided. So domain and range are things that should make sense if you look at the graph. We are now on G. Y is equal to x minus 1 over 2. So the beauty here is we've got a number, just a constant on our denominator. So we can't expect to have a restriction. We are okay having a 0 on the numerator. So all set of real numbers can define this function. That's our domain. For our range, we'll make x a subject. So x minus 1 is equal to 2y. X is equal to 2y plus 1. Anything that is able to perform a restriction on that? Nothing at all. So the expected values of y is a member of real numbers. Okay, so we are able to get even a 0, negative numbers, positive numbers. There is no restriction to this function. You can sketch it to see what's going to happen. So we can give it a try. We see if it's true. I'll get negative 2, negative 1, 0, 1, and 2. Fast. If you plug in a negative 2, negative 2 minus 1 will be a negative 3. Negative 3 divided by 2. If I plug in a negative 1, negative 1 minus 1 will be negative 2, giving me -1. If I plug in a 0, we'll have -0.5. If I plug in a 1, it will be a 0. If I plug in a 2, it will be 0.5. I don't want to deal with fractions. I'm always scared of them. Let's try to see what we're going to have as a graph. So we have -1, we have 0, we have 1, we have 2. So -1 is giving us -1, -1. I believe this is where -1 is. And then 0 is giving us -0.5. 1 is giving us 0. 2 is giving us 0.5. So if you put 3, I believe you have 3 minus 1, which is giving you 2. So it gives us a 1. 3 will be comma 1. So I don't basically know if this function is linear. It looks to me as though it's coming out as linear. Let's see the difference that we have. So it's a difference of 0.5 here. Difference 0.5. I think it's linear. Yeah. So the function is linear. So this function has got there's no restriction on this function. It is going everywhere. So all the values of x can work. Then it's going towards the negative infinity and also a positive infinity. So all the values of y can be found as predicted. No restriction. So when you look at a quadratic function, what comes to your mind? So you know how to sketch a quadratic function, right? So for a quadratic function, for any information, in a case where you have a minimum value, the coefficient of x squared is positive. If you've got a maximum value, the coefficient of negative x of x is the negative. So in this case, we've got a negative, so expect that the function is supposed to be a maximum. So all we have to do for us to find of course, the domain, all the values of x should be able to define a quadratic function, no restriction. Now, for the range of the expected values of x, in a case where you have a maximum, you understand that the minimum is going towards negative infinity. All you have to do is find the maximum value. So we find the maximum by knowing that x is equal to negative b over our 2a. Our b is 2, so the negative of it over 2a. Our a is -1, which is the coefficient of x squared. So we have -2 over -1 giving us 2. 2 is the x value of the turning point. We have to substitute in the function to get the maximum value. So we have a -4 plus 4 plus 7. So we have 2,7. 2,7. So the value of y that is the maximum is 7. So we have all the way from negative infinity all the way up to 7 as our maximum value. That is our range for that quadratic function. If it was a minimum, we'll start from 7 going up. The last one, y is equal to the square root of x minus 3. Is there any value that is able to make that function undefined? Of course, I can think of values that are less than 3. For example, if I put a 2, 2 minus 3 is a -1. So even without solving, I believe the values that can define this function should be values of x that are greater than or equal to 3. Okay, so x minus 3 should be greater than or equal to 0. So if you take it the other side, you get that. So that being a radical function, what happens if you are sketching it? Of course, you understand that in this case, your restriction is that you are starting from the minimum value of 3. minimum value of 3, and that is giving you a 0, and then you start going up. So what's expected values of y? So y is obviously going to be the minimum value of a 0 all the way up to positive infinity. That is our range. So hopefully you know what the domain is and what the range is from what we've talked about. Domain deals with the possible values of x that can define the given function. The range are the expected possible values of y of a function using the given domain predicted. We'll now answer question 5. These are simple questions. So these questions are what we call coming from the aspect of composite functions. So the meaning of f of g of x, it means you can write it in this way for you to understand. Okay. So if you have a function, for example, you have f of x, right? F of x is equal to 2x squared plus 2. So it's kind of like where there's x now, you are putting g of x. That's the meaning. So in a case where you start with g of x, it means the function you're considering is the one that is starting g of x. So for the first part, which is saying f of g of x, it means where there is x, put g of x. So therefore, for f of g of x, which is 2x squared plus 2, where there is x squared, I'm going to put g of x squared plus 2. So our g of x, according to the question, is x minus 1. So I have x minus 1 squared plus 2. At this point, I'm able to expand it. X squared minus 2x plus 1 plus 2. 2x squared minus 4x plus 4 after adding 2 plus 2. So what is our result? And then if we go to the next one, which is saying g of h of x. In such a case, you are considering g of x. Now g of x is equal to x minus 1. So what it means if you say g of h of x, it means now in the function of g, where there is x, you put what? You put h of x minus 1. Now h of x is 3x, so you have 3x minus 1. That's your answer. And then finally, for the last one, we have h of f of x. H of f of x. So our function we're considering is the first one, which is h of x, which is 3x. Now where is x? We are putting f of x. So f of x is 2x squared plus 2. So we have 6x squared plus 6. As simple as that is. We are on B. So B is asking us now for each of the given functions, fg, to find f of g of x and g of f of x. So for the first one, I'll just do this. So here we'll be finding f of g of x, and then on the upper part we'll be finding g of f of x. So I said consider the first function. So where we're saying f of g of x, our function under consideration is f of x. So for part 1, f of x is 2x minus 3. That is our function under consideration there for the first part. Now what that means, if we say f of g of x, it means where there is x now, you are putting g of x. So our g of x in that case is 3x plus 2 minus 3. So we have 6x plus 4 minus 3, 6x plus 1. That's our result. Now for g of f of x, it means the function we're considering is g of x, which is 3x plus 2. Now where there's x, we're going to put f of x. Now f of x in this case is 2x minus 3 plus 2. So we have 6x minus 9 plus 2, 6x minus 7. So we are good to go for the first one. With all these concepts, feel free to pause the video and try the next one out. So for the next one, our f of x is x squared minus x. Now wherever is x, we are going to put our g of x, which is x plus 4. So x plus 4 squared minus x plus 4. Be careful with a negative. So I've put x plus 4 in brackets. So we have x squared plus 8x plus 16 minus x minus 4. I like terms. So I've performed all the calculations. 16 minus 4 is 12. Now on the other part, we are starting with g. So g is x plus 4. Now wherever is x, we're going to put f of x. F of x is x squared minus x plus 4. That becomes our answer. So the key takeaway point is whatever function is starting, that is what you should start with, and the second function that follows, that's what you should substitute. Now for the last one, f of x is 2 over x. Now for us to find f of g of x, where there is x, we would have to put g of x. Now g of x is x minus 3. So we've answered. For the other one, g of x is x minus 3. For us to find g of f of x, where there is x, we're going to put f of x, which is 2 minus x minus 3. So that's how you answer these questions. They are simple and straightforward. Who gets to answer question 6? Very interesting. The functions given below are either bijective or not. If a given function is bijective, find its inverse. If it is not bijective, limit the domain by finding the largest possible subset so that the function is bijective, and then find its inverse. In each case, state the domain and range of a function and its inverse. So we need first of all to understand what the word bijective means. So the word bijective means that the function should be both injective and surjective. So I'm now introducing other terms that you may not know. So injective means one-to-one. Surjective means an onto function. So for you to come this far, you already know what the different relations are. So in a case where I can consider my domain, I cover my input values, usually called x and y. So in a case where I've got 1, 2, 3 as my input, and then I've got, let's say, a, b, and c in my output. So in a case where all the outputs are mapped to something from the input, that, and then there's only one corresponding input value to an output, this is a one-to-one function. So this function that I've written down, it also does qualify to be called an onto because all the elements in the output are mapped to something in the input. Now what happens if I say I introduce in a new element? Let's say we have a 4 there, and then find that the 4 is also giving us a c. So this function is an onto, it's still onto, but it disqualifies to be a one-to-one because we have an output which is mapped to 2 input values in such a relation. Okay. Now, what about an example that is not an onto function? What example can you give? So you know that you can't have an input value without being mapped to any image. That is not a function. Okay. But it's possible that you may have something in the code domain that is not mapped to anything in the input. So this is still a function, but such a function is not surjective, or it's said to be not an onto function. So for a function to be bijective, it's supposed to be both injective and surjective, meaning that's supposed to be first of all one-to-one, and then it should also be an onto function. So I'll show you how to basically know that using both a graph and also algebraically using certain equations. Okay, so we'll start with the first question. So we have f of x is equal to 2x plus 3. How do we basically find whether this function is bijective or not? So we need to first of all show that the function is one-to-one. So by the way, you need to know that all linear functions are bijective. Okay, I'm giving you ideas so that even when you're answering questions, you know. So if you are to sketch such a function, it would be it will be a straight line. A linear function is a straight line. So if you've sketched a function or if you've graphed a function, one way of knowing whether it's bijective or not is by drawing a horizontal line. So if I was to draw a horizontal line parallel to the x-axis, if the line is only cutting the graph once, then that function is one-to-one, and then it is also bijective. Okay, pay attention to what I've said there. Now in a case where I can draw a different function, let's say function something like this. So that quadratic function is being cut by the horizontal line twice at two different points. So that makes that function not to be a one-to-one function. It is not a one-to-one function. Okay, so you're able to test using just a graph. So you're able to tell this is bijective, this is not bijective. Okay, but we can restrict the domain as we'll see later on. So let me show you algebraically how you get to show that the function is injective. So first of all, we need to make sure or prove that this function is one-to-one. Of course, we've seen graphically that it is one-to-one because it is not possible for us to have of course it is possible in certain cases. For example, where we have x squared, you may find that in a case where you are using -3 and +3, they will give you 9 and 9 respectively. So you have two different input values mapping to same output value. So that is not a one-to-one. So if we are to prove algebraically that the function is one-to-one, we need to show that if we can have an input value a giving us c, and then you use also a different input, let's say b, and then it gives you c, this should only happen if a is equal to b, meaning that we shouldn't have a case where we have, for example, -3 and 3 giving us the same result. No, it should only happen if you are using 3 and 3 for you to get the same result, c. So how do you prove that? So f of a, or any variable of your choice, if I substitute in my function there, I'm going to get 2a plus 3. And then if I use f of b, if I substitute in my function, I'm going to get 2b plus 3. So if I get to equate these, 2a plus 3 is equal to 2b plus 3. So I'll be able to see that my 3's will be able to subtract. And then my 2a is equal to 2b, so I can divide by 2, giving me a is equal to b. So the moment I get that point, I've proven that it is a one-to-one function. That's how we prove algebraically. Now, how do I prove that this function is adjective or an onto function? How do I prove that it's an onto function? So for me to prove that it is an onto function, there should be something like, for any point in the range, there should exist a b in the domain. So in a case where you're saying you have, let's say, f of b giving you a, what we should say is, for this a to exist, there must be a b in the domain, meaning that nothing should just exist in the output without adding an input value. Okay, so how do we show that? So we get to show that by basically looking at our equation there. Okay, so say the expected value a, for you to have any value a to be an output, you need to have a certain value of b, which should be part of what? Which should be part of the domain. So if I, to make b my subject in this case, I'll have a minus 3 is equal to 2b, and then a minus 3 over 2 equal to b. So my b, remember that my b is denoting the value of the input. So I'm saying there exists an x value for us to have that a. Okay, and this value, if you look at it, a minus 3 divided by 2 it is definitely going to be a real number, right? So the fact that it's a real number shows that it is part of a domain. Remember, the domain of that inverse function is what? The domain is a set of all real numbers. Whenever you're thinking about the domain, you're thinking about what possible values of x can define the given function. So if you look at a linear function, there's no restriction there. So that is how you show algebraically. So we know that since it's bijective, we're able to find the inverse. So you just get to find the inverse by putting a y with f of x, and then making x the subject of the formula. Okay? So you have y minus 3 is equal to 2x. X is equal to y minus 3 divided by 2. Now for you to write your inverse function, where is x, I'll put f of negative of fx inverse, or use that written as f negative of x is equal to, where there's y, I'll put an x minus 3 over 2. So that is our inverse function. Okay, I believe you now have ideas. I hope you now have ideas. So if you have an idea, you can try out the next function. F of x is equal to x squared minus 4x. Is this function bijective or not? So I'll try first of all algebraically before I get to sketch it. So algebraically, if I look at this, I'll say my f of a will give me a squared minus 4a. My f of b will give me b squared minus 4b. I believe you know how to simplify functions for us to be on question 6. So yes, so we need to show that a and b should be equal if they are to give us the same result c. So a squared, I'll equate the 2, is equal to b squared minus 4b. So at this point, what are we supposed to do for us to basically get to simplify this? Remember, the initial point is always supposed to be, if you equate them, they are supposed to be equal at the end of the day. If they are not equal, then it's not injective, or then it is not one-to-one. So are we able to show that these are going to be equal? So a minus 4, b minus 4. So somehow we can't show that they're going to be equal. So this function is not, it is not one-to-one. Okay, I can't show that a is equal to b. Personally, I have failed to prove that. Now we can look at it graphically. We try to come up with a simple table of values and sketch that function very fast. X, y, let's say we have negative 2. Okay, let me use small values. Negative 1, 0, and 1. So if you substitute in the function where there's x, you put a negative 1, you get a positive 1. And then you get a 5, I believe. Put a 0 there, you get a 0. You put a 1 there, you have 1 minus 4. Right? 1 minus 4, negative 3. We can extend a bit. What if you put a negative 2? Negative 2 squared will give you a 4 plus 8, I believe. 12. Try the other side, 2. 2 will be 2 squared minus 8. 4, that is negative 4. Put a 3 there. 3 squared will be 9 minus, so 12. 9 minus 12 will be a minus 3. So I think those points are enough. So if you have to come up with a graph, the first point we have is negative 2 comma negative 2 positive 12. That is too big. Somewhere there. Then we have negative 1 giving us something like 5, right? Somewhere there. And then of course if you try a 0, it is giving us a 0. And then if you try a 1, A 1 is giving us a negative 3. And then if you try a 2, giving us negative 4. If you try a 3 is equal to 1, so it's negative 3. So obviously this function is going to come out like this. You know that's the way a quadratic function comes out. So if you draw a horizontal line, it's going to cut the graph at 2 points. So that already in itself tells you that the function is not one-to-one, making it not to be bijective. Okay, so you're able to find the minimum value, which or also called the turning point, by using x is equal to negative b over 2a. I believe you learned about quadratic, so you'll be able to find the turning point using that, which is actually going to be, in this case, the one we've seen, 2 comma negative 4. That's our turning point. So this function is not bijective. So how do we make it bijective? Because the question says if the function is not bijective, limit the domain. Okay, limit the domain. So the domain, first of all, of this quadratic function is all set of real numbers. Like every value of a real number that you can put there, you can still get an answer. So we have to restrict it. So look at this part now. So the symmetrical part of the graph, that's where we can restrict this function from. We can restrict it from there. So you can choose a side. Okay, choose a side. So if you do choose a side in this case, if you choose a side, I'll go for the positive part, where I'll say my x value should be greater than or equal to 2. So I've chosen the positive part. Okay, so the range therefore in such a case will be the minimum value, which is negative 4, going up to all positive infinity. That is the expected range. Okay, so let's find its inverse now without restriction. So you basically get to find the inverse by making x subject, which looks a bit complicated. So by the way, for the previous question, I'm not sure if I did find the range. So did you find the range? So the inverse function was what? So whatever inverse function we add, let me just try to remember. If you make x a subject there, what are you going to have? Y minus 3 over 2. Yeah, so kind of we had something like x minus 3 over 2 as our inverse function. So what value do we have? Any restriction? So the fact that we're not dividing by any variable, so I believe there is no restriction on the range as well. So the way I like simplifying this, I say whenever you find an inverse function, just do the same procedure. Look at the inverse function the way you look at a normal function. Find its domain. Now the domain is instead called the range, and then you use the value y of a function itself to give the range. You don't say x. X denotes the domain. Okay, let's focus on the question at hand, which looks a bit interesting. So x squared minus 4x is our function. Now we saw that the function itself wasn't bijective. Now we've restricted the domain to restrict it to x should be greater than or equal to 2. Now if we are to make x a subject in this case, we have to go by computing the square method, where you say, okay, well, what is the half of the coefficient of the bx, in this case, which is negative 4? So the half of that is a negative 2. So we'll add its square on both sides. The next step is you look at x and negative 2, group them. X minus 2 squared is equal to y. Negative 2 squared is going to give us a 4. At this point, it's easier for you now to make x a subject by finding the square root on both sides. So x minus 2 is going to be equal to plus or minus y plus 4. So if you make x a subject, x is going to be 2 plus or minus y plus 4. Now you have to be very mindful to say whatever value that you put in the square root there, it should be what? Whatever value you put in the square root should not give us a negative. That's why if you look at our expected range, we are saying the range is -4 going up, and it's true. So if you find the inverse function, the other way you can look at it is if you look at the square root, there is a restriction that you can't have negative numbers there. So whatever you have under the square root, in this case y plus 4, should be greater than or equal to 0. In such a case, y, which is denoting our range, becomes greater than or equal to -4, which is actually what has been presented as our solution already. So that's how you find the range from the inverse function. So you present your inverse function in this form instead. So of course we have to put an x back where this y. Now we don't have to put plus or minus. Looking at the side that we had picked for restricting our domain, we chose the positive side, right? We chose the positive side. So if we chose the positive side, then we remove the minus. Okay. So that's where we are. We found our inverse function after restricting the domain. So the range has already been found, the domain has already been found. We are now on the third question. F of x is equal to x over x minus 3. So the best way of approaching this question would be to sketch it. Okay? We need to sketch this simple rational function that we have. So the fastest way of sketching these rational functions is first of all finding the vertical asymptote. So if you look at the denominator there, what value of x will make this function to be undefined? Of course, we know that we shouldn't have a 0 on the bottom. So x minus 3 should not be equal to 0. So therefore, x should not be equal to positive 3. So that becomes our what? Our vertical asymptote at 3. Okay, quickly we can find the horizontal asymptote by finding the inverse, which I believe we're able to. That in itself is proof enough that this function is bijective. Okay, it's already bijective. Because if you look at the values of the powers of x, we don't have an even power, so expect that all the results will be unique by themselves. So y is equal to x minus 3, cross and multiply xy minus 3y is equal to x. We're trying to make x a subject, so we can take x on one side. So if you factorize the x, you have 3y over, if you factorize out the x, you have y minus 1. So y minus 1 is the denominator. So the restriction on the value of y will be y should not be equal to 1. So y should not be equal to 1. So that becomes our asymptote, our horizontal asymptote. Okay, that is 3. So the function expected, I believe, should be something like this, and then something like this. You can try to sketch. So those are just, I'm just making assumptions. Yeah, likely will come out like that. Okay. So if you try any value in that function, let's say we try a value 4, is it true that it will be above the x-axis? 4 over 4 minus 3 will give us a 1, which is true. So I'm right. That's the way we expect this. So is it true that if you draw a line, a straight line, horizontal line, that is going to cut the graph twice? No, it's not possible. So this function is bijective. Is 1 to 1. Is 1 to 1. The function is 1 to 1. Now, what's the domain, first of all, of that function? So the domain is that x should be a member of real numbers, first of all, but x should not be equal to 3. Okay, that's the argument there. So now the question is it that every time you look at that function, you expect to have a certain value of it? Okay, so how do we prove that it's an onto function? So the graph has already proven it's a one-to-one function. So what if we say we have f of b is giving us a. Now we are saying for any value of y a, there should be an equivalent value of b which should be part of a domain. So let's try to see if we look at that function which is x over x minus 3. So if I put b, I'll have b over b minus 3, which is equal to my y. So the value of y is a. So we try to make b the subject. So I have ab minus b is equal to 3a. Factorize b, you have a minus 1. So giving us our value of b being equal to 3a over a minus 1. So is it true that the value of b that we found is part of a domain? 3a over a minus 1. That is a real number, right? So that is proof enough that this function is an onto function. For every value of a that is existing as y, there should be a possible value of b being part of a domain. So this function is an onto function. So it is a bijective function. We've already found the range. The range will only add a restriction to say y should not be equal to 1. But all the other numbers, it is possible. So that is how you basically get to sketch rational functions, be able to find the domain. So there was no restriction that we needed to make to that domain. Of course, if you look at d is very simple. This is a linear function that we're from talking about. So the expected domain is a set of real numbers. So it's a bijective function. It's linear. Remember, if you draw like that, there's no way you're going to have a horizontal line cutting that linear function twice. So you're able to find the inverse easily by making x a subject. So it will be y plus 2. Let me take them on one side. So x is going to be 2 minus y. So f of negative of x is equal to 2 minus x. That's the inverse function. Let's look at e now, which is now a radical function. Is that function bijective? Now, every time you have a square or any even power, you'd have to be suspicious now, because those ones are not usually going to be bijective, because if you use a negative and a positive value, they'll give you the same value at one point or the other. Okay, so we can try to sketch this function. We can come up with a table of values first. Okay, so first of all, we understand that whenever you're looking at that, how do we find the domain? Let that be our first attempt. So a domain is that whatever is under the square root should always be greater than or equal to 0. Okay, now that is the difference of two squares, because 4 can be expressed as 2 squared, so it will be x minus 2, x plus 2, greater than or equal to 0. So we can solve that as an inequality. So we can get the zeros at the points where x is going to be equal to 0. So it's at x is equal to 2, negative 2, and then at x is equal to positive 2. So we have to find whether it's the numbers in between or outside this range will satisfy that equation. So if I get a number in between a 0 there, I put a 0 where there is x, I'm going to have negative 2 multiplying with 2, which will give me a negative 4. Now is the question, is negative 4 greater than or equal to 0? Of course not. So since that has refused, we expect that the outer part will agree. So I can try negative 3. If I try negative 3 here, I plug in there, I'll get a negative. In there, I'll get a negative. So I'll get a positive, which is greater than or equal to 0. So this has worked. I expect that to work as well. So therefore, the domain will be x should be First of all, less than or equal to 2, and then what else? Not necessarily less than or equal to 2. These are greater. So x is greater than or equal to positive 2, and then x is less than or equal to negative 2. So those are the two. Well, that's the domain for this function. Then you can express it as actually from negative infinity all the way up to negative 2, and then you unionize it with the other part all the way from 2 going up. That's another way of presenting your domain. Now, the question is, should we make any restriction to that domain if we are to get a bijective function? So I said, let's try to sketch a function. So table of values, let's say x and y. Remember, we are using numbers negative 2 less, and then numbers positive 2 higher. So I can, if I use negative 2, I will get what? A 0. If I use positive 2, I'll get what? A 0. I can get a number in between. The numbers in between are not working. They refuse. So we can go to higher numbers. What number can I put there? If I put a 3, it will be 9. 9 minus 4, I don't want that. If I put a 4, 4 squared will be what? 16 minus 4, 14. So the way this radical function is going to come out is like this, by just looking at the starting point. So first of all, expect that no negative results will be produced from your square root. We only expect positive results. So we are starting at positive 2 and a minus 2. So the fact that it's a radical function, we expect it to be going up only. So this one will go like this. This one will go like this. Okay, you can try that. So if you put something like a 3, 3 squared would be 9 minus 4 to the root of 5. Okay, root of 5. You try 4 root of 14, so it will continue going up and up. Now, if you draw a horizontal line, you find that it will cut the graph twice, right? It's possible to cut it twice. So that is not a one-to-one function, making this function not to be bijective. So we can restrict it. We can restrict our domain. So it's either we get this side or we get the other side. So we'll just get the positive side. So we'll say our restricted domain will be x should be greater than or equal to 2 if we are to have an inverse. We've restricted it to that domain, else it won't work. Okay, so we're only remaining that part of the function. So how do you find the inverse function? So inverse function, of course, you just square both sides, because you're going to say let y be equal to the square root of x squared minus 4. So if you square both sides, you're going to have y squared is equal to x squared minus 4. Your goal is to make x a subject. So you have y squared plus 4 is equal to x squared. So you square both sides. You find the square root of both sides. So your x is equal to that, root of y squared plus 4. So in terms of presenting your inverse function, you take back your x where there's y. X squared plus 4. So that's the inverse function. Now the range, what is the expected range of values to be produced? So if you look at the graph, the minimum value we have is a 0 for the y, going up. So that's the range, 0 all the way up to positive infinity. Okay, with a restricted domain. We now have the other rational function there. How do you look at it? So by the way, if you're tired, please feel free to pause the video, take a walk, and get back to watch. You can download it as well. and watch it later. So if you have some more energy, try this one out. So y is equal to 1 over x minus 3. So the first restriction I'm seeing is that x of course should not be equal to 0. So that already gives us the first it gives us a vertical asymptote. Vertical asymptote. So x should not be equal to 0. So the y-axis itself is the vertical asymptote, because the equation of the y-axis is x is equal to 0. Then we need to find the what? The horizontal asymptote by making x a subject. So the fact that we're able to make x a subject in itself tells us that this function is bijective. Not necessarily that it's always the case, because we saw that in this question, despite us being able to make um, x a subject, it was still not bijective. Okay, so usually these functions not having the even powers are not bijective. They are usually bijective, sorry. So 1 over x, cross and multiply, we have xy, 3x is equal to 1. Our goal is to make x a subject. We factorize our x, we have y plus 3, y plus 3. So x is equal to 1 over y plus 3. So the value of y that can make the denominator to be equal to 0 is obviously going to be negative 3. So negative 3 becomes our horizontal asymptote. So how do we expect our function to behave? So it will be something like this, and then something like this. So these rational functions with the asymptotes, it's not possible for us to have the line cut them twice, right? So this function is injective or one-to-one. So expect this function to be bijective, right? In case where they want us to prove if it's an onto function, you can as well try it out, where you say, okay, for every value of a being produced, there should be a value of b which is part of a domain. So remember, the domain is x is a member of all real numbers, but only x should not be equal to 0. Okay, first of all. So by the way, don't forget that we've already found our inverse, right? I hope you've not forgotten. So our inverse was 1 over x plus 3. So for every value of, let's say, c being produced, there should be a certain value of b part of a domain. So you can just put b there. So you have 1 over b minus 3, giving us a value of c. You make b the subject. So your b will be actually equal to 1 over c plus 3. So the question is this right hand side part of the real numbers? Of course it is. So that's already proof that this is an onto function. So this function is bijective. We don't need to make any restrictions for us to get to an inverse. And then you are finally on the last one. Just make sure and ensure that you've understood everything. You can try it out. So the domain, of course, will be a set of all real numbers with a restriction on the denominator. X should not be equal to 1, because if it was going to be equal to 1, we'll have a 0 on the denominator part. Is a function bijective? So if you try to sketch that function, it will not, it will also come out as the other rational functions have been coming out. So you can try it out actually. So it is a bijective function after sketching. Okay, so I've told you how you are basically able to tell from the graph if a function is bijective or not, or whether it's injective or not. So how do you find the inverse? Say y is equal to 3 over x minus 1. So yx minus y is equal to 3. Your goal is to make x a subject to the formula. So xy is equal to 3 plus y. X is 3 plus y over y. So already we're able to sketch this graph. So the horizontal asymptote is y should not be equal to 0. Wait. Yeah, y should not be equal to 0. Y should not be equal to 0. So I believe that is the x-axis. And then the vertical asymptote is x should not be equal to 1. So we expect the graph to come out this way. So already you're able to see that you can't actually have a point where the horizontal line is cutting the graph twice. So no need of us to restrict the domain. So our inverse function will just be 3 plus x over x. So that's it with question 6. Question 7 is saying explain why a straight line parallel to the x-axis will intersect the graph of a one-to-one function at most once. So what we need to understand is for a one-to-one function, the basic argument is that for you to have a one-to-one function, there must be at most one input value giving you a y value. So if you, let's say you have x and y, if in the y you've got a 2, this 2 should only be produced by a single value from the x values, never 2, never more than 1. That's what a one-to-one function is. Okay, now if you look at a one-to-one function, the basic example you can think of is a linear function. So if you draw a line parallel to the x-axis, that line, yeah, I'm trying to make the explanation simple. So if you draw a line parallel to the x-axis, that line is moving along the same value of y. If let's say it's cutting at y is equal to 2, that is the way it is moving. It is having the same equation, y is equal to 2 throughout. So it can only cut a one-to-one function once, because the one-to-one function, for each single value of y, it only has a single value of x. So for example, if I was to draw a certain linear function, let's say like that, so that linear function that I've drawn, which is a one-to-one function, has only a single value of x that is giving us a value of a 2. So a one-to-one function has only a single value of x for every value of y. And the fact that a horizontal line parallel to the x-axis has only a single value of y, it will only intersect the graph once. I don't know if that makes sense, but that's a basic argument behind that. Question 8, we need to determine whether the given functions below are even, odd, or neither. So the basic argument here is, for an even function, the function itself should be equal to the function of the negative value of x. Meaning that for an even function, it doesn't matter whether you are working with a positive value or a negative value, the function behaves the same way. Okay, that is for an even function. For an odd function, the negative of a function is also equal to the function of the negative value of x. So we'll start with a. A is 1 minus x squared. So that is the function itself, f of x. F of x is equal to 1 minus x squared. So I like starting by testing whether it's an even or not. So I'll say the function of negative x. So where there's x, I'll put a negative value of x. So after I square it, it will still be x squared. So they are equal. So we can say f of x is equal to what? We can see that it's equal to a function of the negative value of x. So By the way, you are even able to expect that by looking at the powers that you have. The fact that we've got even an even power, we expect that the function is going to be even. Okay. All right. So that's an even function. You don't even have to test the other one. If you try to be an odd function, it won't work. Okay. Let's try B. For B, we have f of x being equal to. So I expect that one to be an odd function because it's a combination of an even power and an odd power, which is a 1. So f of negative x, for x squared, if I put negative x squared and then minus where is x, I'll put also negative x. So what I'm getting is x plus x squared plus x. So there's a difference in terms of a sign. So it is not an even function. So I will straight away go and try negative of f of x. So negative f of x means you multiply the original function by a negative. So it will be negative x squared plus x. So it has also disagreed. There is no agreement. So it's neither even nor odd. Then we are on C. C is a quadratic function. f of x is equal to 3x squared plus 2x minus 1. We need to determine whether it's even or odd function or neither. So of course f of negative x would mean where there's x would have to put that. So 3 negative x squared, and then where there's x, we're putting negative x minus 1. So we are going to have 3x squared minus 2x minus 1. Any agreement? There's no agreement. Negative f of x, multiply the original function by negative, so I have negative 3x squared minus 2x plus 1. So no agreement again. So this function is neither odd nor even. And then the last one, we have x plus 1 over x. That's for f of x. We can quickly try f of negative x. So always x, will put negative x, and then that has already disagreed, and then we'll try negative f of x. So I have negative x minus 1 over x. So we can see that the two have now agreed. So this is the only odd function we found, because f of negative x is equal to the negative f of x. So the key takeaway point is pay attention to these two conditions. That's for an odd function and even function. For question 9, the diagram below are graphs of real functions. So we just need to identify which one of these are even or none of the two. And then which of these graphs represents functions that are one-to-one, and then justify your answer. So I'll give you some tips to help you identify functions. So whenever a function is symmetrical about the x-axis, okay, whenever it is symmetrical like this one about the y-axis, and then you have like a mirror, meaning that the left side looks exactly like the y-axis, that is an even function. Okay, whenever you are able to cut into half using the y-axis, and then you are able to the half, okay, it's like an image of the other side, it's an even function. Now whenever you're able to draw a horizontal line parallel to the x-axis, if it cuts a graph twice, then it's not a one-to-one function. Okay, so this function is not one-to-one. First of all, how are we going to justify our answer? So we'll say because we have two values of x giving us the same value of y. Okay, if you got the second one, is it also the case that if we cut this graph, is it also symmetrical about the x-axis, the y-axis? Is it that the left hand side is also equal to the right hand side? So this is matching up, that is matching up. So that is also an even function. It qualifies. It's matching up. It's exactly the same on the left and the right. Is it a one-to-one? Of course, if we draw a horizontal line, it will cut the graph more than actually even twice. So it's not a one-to-one function. If we go to C, if we observe about the x-axis, is this symmetrical? It is not symmetrical. It is not symmetrical. But what is on the left and the right are the same, but it's not an image. Okay? It can only be an image if this part was to be on top like that. So a function where something is symmetrical, or where the left and the right hand side are the same, of equal size, but not mirrors of each other, that is an odd function. So this function is said to be an odd. It is symmetrical but not mirror. It's not like an image of the other. We can go to, first of all, is it one-to-one? So equally for that one, if you draw a line, it will be able to cut the graph at more than 2 points. So it's not a one-to-one function. D. If you look at D, is this graph symmetrical about the x-axis? No, it is not. But is what is on the left and the right hand side about the same size? Yes, it is. This is the same with what is on the other side, like this. Okay, so what can you say then? So that is also an odd function. Equal size on both ends, but not exactly an image. So it's an odd. One-to-one, draw a line, it's cutting it more than once, so it's not. For this other one as well, it is of equal size but not images, so this is also said to be an odd function. Is it a one-to-one? If I draw a line, it is only cut at 1 point. So this function is one-to-one. The last one, symmetrical about the y-axis, mirror image of one another, so it's an even function. I draw a line, it's not a one-to-one function. So that is how you look at, if you are given a graph, determining whether it's a one-to-one is very easy. Determining whether it's even or odd is also very easy. Okay, of course, in a case where it is the left side and the right side are not the same, and they are not even images of each other, such one will be neither odd nor even. It seems obvious that have been given are of equal size on the left and the right. So that's it to this video. I hope you've learned most of the concepts and the functions, and you're good to go.